Swayam Prabha. Digital India. Educated India.
So now let's look into the algorithm. So in this algorithm, like the quadratic function, we have to choose the start point x1, a small number epsilon f, which represents the precision which we want to achieve, a step size s. At this particular point, we are going to find out the first order derivative, which is here, and we want to set the counter k is equal to 0. Now, if we find the first order derivative representing the slope of the objective function at the first chosen point is greater than 0, indicating the slope is positive, that means my second point should be somewhere lesser than the x1 value, and for that reason we are saying x2 is equal to x1 minus 2 to the power k times s. This particular equation is familiar to you. We use this one in the bounding phase method. If the slope of the objective function at x1 is going to be less than 0, which is the negative slope, that means we are going in the direction where the objective function is going to further reduce. So we need to add this with x1 and get the x2 value. Once we get the x2 value, we can calculate the slope at the second point. Now, once we get the slope, we want to ensure that the slopes which we have at these 2 points are of opposite in nature. For that reason, we are checking in the third step that if we multiply the slopes of the both points, then it should be less or equal to 0. If it is not, we need to go back by setting k equal to k plus 1 into the step 2 to find a point where we can obtain the slopes which are of opposite in nature. So these 3 steps are not needed if you have already bracketed the optimum point, and in the bracketing process we are very clear that the optimum point is going to lie somewhere between the 2 brackets or 2 extreme edge of the bracket we have identified. So those 2 extreme edge are going to serve as x1 and x2 for the problem, and we can move ahead with that particular point. Now, once we know this x1 and x2, and if we can estimate the first order derivative at those 2 points, then we can find out the optimum point for the cubic function, and that is going to be x star, which you have seen in the previous slide. Once we do that, we are going to find out the objective function value at that particular point. Then we are going to compare that objective function value with the objective function value of the first point. If we find that the objective function value of the new point is lesser than the objective function value of the first point, then definitely the point is better and we can move further in the next step. Otherwise, we have to get closer gradually towards the first point until we find a point where the objective function value is going to be less than the first point. Once this is obtained, we need to find out the slope at this new point. If we find the slope is less than the precision we want to achieve, then we can terminate right there. And once we terminate, we need to report the optimum value, which is going to be x star, and the corresponding objective function value. If we are not terminating because the slope which we obtained is still not within the precision value, it's higher than that, then we need to change the boundary. For that, we need to check the slope at x1 and the slope at the new point. If we find these two slopes are of opposite direction or opposite sign, then definitely it is going to be less than 0, and in that case we can say that the new x2 is going to be the point which we have just evaluated. And for further process, we need to go to the step 4, where again we are going to find a new point based on the cubic function, and the process continues. If we find that the slope at x1 and the new point are of similar nature or of similar direction, then we can move the x1 point to the new point. So x1 will take up the new point as the new boundary, and then we go to the step 4 and the process continues until we reach the termination criteria. So let's look into an numerical example to understand this method. So we are using the same objective function, which is this. We are starting from an initial guess which is x1 equal to 0, and as I had said, if we know the bracket already, then we can use that. Otherwise, we have to use some method. In this case, we have shown you that we are going to use the bounding phase method to come up with an boundary where the slopes are going to be of opposite nature. So in this case, if we are using one single initial guess, we are using the step size of 1.5, and efficiency we are setting it as 0.2. and then if we are looking into the first point, based on the first point, if we are looking into the second point, which is going to be 1.5, we realize that the slope at the first and the second point are of same nature, which means if we multiply it is not less than 0, so we cannot proceed. We need to move to the another point where we using the bounding phase method. So here the first point is the 0.00, and the second point, based on the increasing order of the bounding phase method, is going to be 3.0. This is exactly the boundary conditions which we used in our previous problems. And once we set it to 3.0, we'll see that the slope at this particular point for the objective function has a opposite sign of the slope which we have at the first point. So we are good to go from here. Then we are estimating the z value, w, mu, and then we are estimating the optimum point for the cubic function, and for this particular point we are estimating the function value of the given objective function. Then we are checking if this objective function value is better than the objective function value of the first point, and it is very clear that yes, it is better. So we go for the first order derivative or look into the slope, and then we compare the slope of this new point with the first point, and then realize that these 2 points are not of opposite direction, which means my new point is going to be the new boundary replacing the x1. So this new point, we are taking it as x1, x2 remains as is, and then when we compare, we see that the slope at the two locations are of different nature or opposite sign. So we continue with the calculation of z, w, mu, which yields a optimum point for the cubic function, which is 2.04. At this point the objective function value is this, and we find that the objective function value actually improved compared to the first point. Hence we move further, look into the slope, and based on the slope we find that the slope of the optimum point and the first point are opposite in sign. So since those two are opposite in sign, so the x2 boundary is revised. Now you will see that the x2 is going to be the optimum point, which is 2.04, and x1 we are retaining the same point. Based on these 2 points, we see that the slopes are of different sign. So we move further, find out the z, w, mu and the x, c optimum point of the cubic function, and at this optimum point we find that the function value of the given objective function, and this objective function value has improved compared to the first point or x1 point. So we look into the slope. Slope is reasonably low, which is actually lower than the precision which we want to achieve. So we can stop right here and report this as the optimum point and this as the optimum objective function value. Now let us look into this method into a graphical representation. So this objective function can be represented by this blue line between 0 and 3. So we started with 0 and the first point we obtained was 1.5, and when we compared the slope here and here, both are of same sign, so we could not use this particular point, so we had to move to the next point. So the next point we had selected was 3, so 0 and 3, and if we compare the slope at these 2 points, it is very clear that the slopes are of different sign. So we can continue with these 2 points, and as we continue we obtain the optimum point for the fitted cubic function as 1.8, which is somewhere here. At this point we found out the objective function value of the given function is lesser than the objective function value at the first point. So we moved this first point to here. Now all this region is eliminated in the process, so we try to fit a cubic function between this point and this point, and once we fit the cubic function, we found out the optimum point now for this cubic function is going to be 2.04, which is somewhere very close to here. This objective function value is better than this particular objective function value, and this is also better than this. However, if we see that the slope here and the here are of opposite sign, hence we are going to replace the x2 point, which is here, will move in this direction. So this becomes my new x2, this was my x1. So once we use this 2 as the point and feed the cubic function, then we can see that the optimum point of this cubic function, which passes through these 2 points, is going to be at this 2.00, and we found that the slope is also within the precision level we have set. So we stop the process right there and report this point as the optimum point, and the function value here is the optimum function value for the given objective function. The two methods we discussed today used a mechanism to interpolate a point between the boundary points, and to interpolate we used either the quadratic function or cubic function. Once we use a quadratic or a cubic function, it becomes a very standard process to find out the optimum point for a known quadratic or cubic function. So that point helped us to evaluate the given objective function and reach closer to the optimum solution. In the quadratic function, we saw that we only need the evaluation of the objective functions. We do not require to estimate the derivatives of the objective function. So the method is actually derivative free or without derivative interpolation method. However, in the cubic interpolation method, we use the cubic function, and in order to find out the optimum point of the cubic function, we had to derive the first order derivative of the objective function and then obtain the optimum point of the cubic function. So technically the cubic interpolation method is an interpolation method with derivatives. In the next lecture, we'll see more such examples where we would need derivatives to interpolate points and obtain the optimum solution or reach closer to the optimum solution. In today's method, if we understand clearly, we see that we are approximating the given objective function with another function. One is of quadratic nature, another is of cubic nature. So by any chance, if our objective function is not at all close to one of the standard format of quadratic or cubic function, then this estimation process may not work that well. The other methods which we are going to discuss in the next class, we'll see that we do not need to approximate the given objective function into another function. So those methods may be better in cases where the objective functions are more complex and not closer to any of the standard format of the function. So with that, thanks to all of you and see you in the next lecture.